In this work, we present a novel data augmentation technique designed for low-resource datasets, specifically tailored for mixed reality applications in industrial settings. Mixed reality applications are becoming increasingly essential in Industry 4.0, where complex industrial environments present various challenges. Object detection models improve with larger datasets, but manual image collection and annotation are impractical. To solve this, we've developed an automated image composition diffusion pipeline that generates annotated images. For the image composition, we created a pipeline that generates prompts, inverts images, and then composes images via parallel diffusion while blending latent spaces while preserving both images in respective masks using different losses. For a seamless image composition as mentioned in the pipeline, a UI was developed that lets users either capture new images, acquire them online, or generate through stable diffusion, enabling precise image generation for model training. This pipeline allows users to easily capture images and automate the augmentation process by blending them with different backgrounds. It streamlines traditional methods, reducing manual labor while ensuring accuracy and efficiency in object detection and background variation. Users select foreground and background images, and the system generates composite images that return to the UI with bounding boxes, enhancing both training and the overall user experience. The process supports seamless integration, allowing users to explore various image combinations in real time. This enhances model robustness by providing diverse scenarios, improving object detection performance and user engagement with the system. We then compared our model with models tuned on traditional augmentation technique and GAN augmented dataset and found failure case. We then tested our model on an MR application for assembling a pneumatic cylinder, in 3 different conditions. In the first condition, the task was performed in a well-lit and uncluttered environment, 79 lux. The model guided the user through the assembly process by highlighting the components to be assembled in green, while a yellow arrow directed the user to the next part. This straightforward scenario allowed for smooth and efficient task completion, with the user confirming satisfaction at the end. In the second condition, a more complex, cluttered environment with the same lighting conditions, 79 lux, was introduced. Despite the added difficulty of multiple objects in the workspace, the model accurately identified the necessary components for assembly. The same visual cues, green highlighted parts and yellow directional arrows, continued to guide the user effectively. The clutter did not hinder the model's performance, demonstrating its capability to handle more challenging and visually busy settings. The third condition presented the most difficult scenario, combining a cluttered workspace with significantly reduced lighting, 9 lux. In this low visibility environment, the object detection model still performed well, accurately identifying and guiding the user to the correct components. Despite the poor lighting and increased visual complexity, the model's green highlighted parts and yellow arrows ensured the user could complete the assembly correctly. This scenario illustrated the model's ability to maintain high accuracy and effectiveness even in less than ideal conditions, showcasing its robustness and versatility in real-world environments where lighting and visual clarity may be compromised. Overall, the model consistently guided the user through the assembly process under all 3 conditions, proving its efficacy across a range of challenging scenarios. We also tested the MR application on a disassembly use case involving the landing gear of aircraft. The task required disassembling 4 key parts: the tire, torque link, oleo strut, and shock absorber. Using the HoloLens 2, the user captured images that were processed through a YOLOv8 model, which was fine-tuned on synthetically generated data. After model inference, holograms of the detected components were rendered and manipulated through fingertip gestures. The MR interface offered 2 options: explode to disaggregate components for disassembly and combine to return them to their original configuration. This showed the efficacy of MR application in outdoor setting with a robust object detection model.